Hello students, this is the Common Core Geometry Instrument Assessment 2 review. We're going to be talking about triangles, we're going to be talking about congruent triangles, similar triangles. We got some coordinate proofs in here. Let's get started. Taking a look at question 1, a line segment has endpoints 3, -5 and 9, 3. What's the length of the segment? You're going to remember the distance formula that we learned about in a unit prior to today. So I'm going to pull up the formula now. Of course, you should recall this distance formula being x2 minus x1 squared plus y2 minus y1 squared. These x's and y's come from the points that are given to you. The first point that they give to you, we're going to label as x1, y1. This is x2, y2. So wherever you see this x2, we're going to replace it with 9. x1, we're going to replace it with 3. And then that minus sign is going to come through, right? So this is going to be 9, x2, minus 3, x1 squared plus, and then y2 is going to be 3, and then minus. y1 is -5. I'm going to put -5. There's still going to be a minus here, and then take that quantity and square it. So there's your distance formula, 9 minus 3, right, the 9 minus the 3, and then 3 minus -5, 3 minus -5. We're going to simplify this, and we should be able to get the length pretty easily. Yeah, the calculator just eats this up, right? 9 minus 3 is 6, 6 squared is 36, 3 minus -5 is 8, 8 squared is 64, so 36 and 64 is 100. The square root of 100 is 10. So there's your correct answer. 10. Not too bad. Moving on, point P. Oh, get out of here, calculator. Point P is on RW such that RP to PW, this is a ratio, is equal to 2 to 3. If R is these coordinates and W is these coordinates, what are the coordinates of P? You could use the coordinate grid, but I'm going to show you how to do it using the partition formula. Here's your partition formula. You got x1 and x2, y1 and y2, just like the distance formula. So we're going to get them from here and here. Another addition that you have here is A and A plus B. This first letter here in the ratio is A, and the second letter in the ratio is B. So we say from A to B. So anywhere I see A, I'm going to put 2. Anywhere I see B, I'm going to put 3, and then you'll see how it gets filled out. So my x1 turns out to be -4. 2 over 2 plus 3 because A is 2, and 2 plus 3 is coming from the A plus B here. 6 minus -4 because x1 was a -4, and then the 20 minus 5 comes from the 20 and the 5 from y2 and y1. The 5 comes from the y1. Like, it's just substituting into this formula, okay? We're going to simplify this now. Here you can see I took 2 over 2 plus 3 and turned it into 2 over 5, which is the same as 0.4. You can see that on the calculator. 6 minus -4 is 10. 20 minus 5 is 15. Everything else basically stayed the same. Now we're just going to do the math to find the actual coordinates of P, that partition point. And you can see I can just put that part into the calculator. I get 0 and 11. So P, my partition point, is 0, 11. This is a formula that you're going to need to know. This is the partition formula. Moving on to question 4. What's the slope of the line that's perpendicular to the line whose equation is 6x plus 5y equals 4? My first step is to solve this equation for y to get the slope. And then a perpendicular slope is going to have negative reciprocal, is going to be a negative reciprocal to the prior slope. I'll show you the first step first. First, we're going to solve the equation for y so we can find the slope. So get y by itself. We're going to subtract 6x from both sides. We get -6x plus 4. And then we're going to divide both sides by 5. We're dividing it by 5 so we can get y by itself. When I do -6 divided by 5, I get -6/5. That's going to be my slope. And 4/5, 4 divided by 5 is going to be my y-intercept. So now it's asking for the slope of a line that is perpendicular to this line. And you'll remember that perpendicular means they have opposite reciprocal slopes. So the slope of this line at present is -6 divided by 5. That's the slope that's there. We need a perpendicular line, and you know that perpendicular means opposite reciprocals. So we're going to turn this slope into the opposite reciprocal by flipping it upside down and turning it into an opposite sign. So I'm going to put 5 divided by 6. And at present, the slope is negative. So when we change it to its opposite reciprocal, it is now positive. So my correct and complete answer is 5 over 6. There we go. Moving on to question 5. Write an equation that represents the perpendicular bisector of CD, whose endpoints are 4, 1 and -4, 5. It looks like this is a several-step process. My first step is going to be to find the slope between these 2 points. I'm going to use the slope formula. Then I'm going to find the perpendicular slope. And since it's a bisector, we're going to need to find the midpoint as well. A bisector is a line that passes through a line segment at its midpoint. So it looks like it's a several-step process. Let's do the first step first. Our first step is finding the equation's slope. So from here, x1, y1 to here, x2, y2, we have a slope of -1 over 2. That's coming from this formula here. So the slope of the line is -1 over 2. The next thing I need is to find that perpendicular slope, and as you recall from the previous problem, perpendicular just means the opposite reciprocal, so we're going to flip it upside down and make it the opposite sign. Fairly straightforward. A perpendicular slope just means we flip it upside down and make it the opposite sign, so negative 1/2 becomes positive 2/1. My next step is to find the midpoint because a bisector splits a line segment at its midpoint. Here's the midpoint formula. So there's our midpoint formula, x1 plus x2/2, y1 plus y2/2. I substitute in the x1, y1, x2, y2 here, and I got m is equal to 0, 3. M, capital M, is the midpoint. That is not to be confused with slope, which is lowercase m. You can see that here. So the next step is to find the equation of the line. We have the slope of the line already. This is the perpendicular slope. We know that since it's a bisector, it has to pass through this point, the midpoint, 0, 3. So what we're going to do is we're going to solve this equation for the y-intercept. We know, and a linear equation is y equals mx plus b. And it turns out we have the m, that happens to be this slope. And we have the x and the y, that's this x and this y from the midpoints, right? Because the midpoint has to be on this perpendicular bisector. So the only thing we're going to be missing is b. We're going to solve for b. So we substituted in 3 for y, 0 for x. The slope is 2/1. That multiplication was pretty easy, so we solved to get 3 is equal to b. Now it's asking for an equation. The equation is going to be made up of 2 parts. That first part is the slope. The second part is the y-intercept. And, well, check us out. We have our slope and our y-intercept here. And there's our correct and complete answer. You'll notice that this 2 is the slope. 2 divided by 1 is just equivalent to 2, so I simplified it here for the answer. For number 6, what is the measure of the largest angle in the triangle containing these angles, x plus 10, and 2x minus 6? You must draw a picture for this because there's no picture here, but luckily for you, you just draw any old triangle. See? I drew the triangle all by myself. No straight line tool used at all. Anyway, the angles are x plus 10, and 2x minus 6, so they go in any of the angles, doesn't really matter. And you'll be pleased to note that the thing that you learned at the beginning of the year still applies. The sum of all interior angles of a triangle is equal to 180 degrees. So x plus 10 plus 2x minus 6 should be equal to 180. You should remember this from when we did it in October. So here are the 3 angles. 1, 2, 3. All 3 angles are equal to 180 degrees. Now we're just going to combine like terms and solve for x. And you'll see x plus 2x, that gives us 4x. And then 10 minus 6, that's going to give us 4, that's equal to 180. So we found that value, which was x is equal to 44, but we're not done because the question does ask us to find the measure of the largest angle in the triangle. The first one's easy, x is equal to 44, we just solved for that. Now what we have to do is take our information and substitute it into the other 2 angles to see what measures they have. So it looks like 44 plus 10 is going to give us 54, so this angle is 44, this angle is 54, and this angle is the last one that's left over. Let's find this now. So 2 times x, which is 2 times 44, is 88. Minus 6 is going to be 82. Looks like the measure of the largest angle of the triangle, therefore, is just going to be 82 degrees, right? 82. And make sure that you're calling it degrees because that's the measure of an angle. Moving on to the next question, question 7. In the diagram of ABC below, we have BD drawn to side AC. This doesn't tell us anything particular about what type of line this is, but it just tells us that BD is a straight line and it's intersecting this line AC. It tells us that the measure of angle A is 35, the measure of angle ABD is 30, and the measure of angle C is 60. Let's label the diagram now. So now it's asking some questions about whether ABC is obtuse, whether the triangle is equilateral. So what we need to do here in order to figure out all of these is find the rest of the angles, and then we can classify these triangles as whether they're equilateral, scalene, isosceles, etc., etc. So the first angle that I'm going to find is this angle here, which is angle ADC. I'm going to use a red dot for that. Angle ADC is part of this triangle. ADB, hopefully I said ADB, not ADC. I think I messed it up before, but yeah, this is angle ADB here, and since this is a triangle, all 3 angles here should add up to 180 degrees. And using that triangle sum theorem, we're able to say that angle ADC is equal to 115 degrees. Now the next angle that we're going to try to find is this angle down here. You can see that this is a straight line. ADC is a straight line. Since it's a straight line, it's got this angle attached to it and also this angle attached to it. That's going to be supplementary angles. They are angles that meet at a vertex and form a straight line. That means that this angle here is going to be added to this angle to make 180 degrees. So knowing that they're supplementary angles, I have 115 plus something is equal to 180. That something is 65. So this angle down here is 65. And then we're not done because we are still missing one angle up here. This angle, triangle DBC, is going to help us find. Triangle DBC is another triangle, so the triangle sum theorem kicks in again. Angle plus angle plus angle is 180, and we know two of these angles, we just don't know the third. Another nice and easy triangle sum theorem, 3 angles equal 180. So one of them is 65 down here, one of them is 60 down here, and DBC is the one we don't know. Subtracting these 65 and 60 from 180, we should get 55. So our missing angle, 55 degrees. So let's go through and try to answer one at a time. It says measure angle ABC is obtuse. Angle ABC is made up of a 55 degree angle and a 30 degree angle. 55 and 30, according to my calculations here, 55 and 30 are 85. 85 is smaller than 90, so the measure of angle ABC, which is 85, is not obtuse. It is an acute angle. Remember, obtuse means greater than 90 degrees. There's the note there. So the next one says triangle BCD is equilateral. From B to C to D, it looks like this triangle has angles 55, 60, and 65. Doesn't match with equilateral because if the triangle were equilateral, then it would be equiangular, same angles. And all of these angles are different. There's a 65, there's a 60, and there's a 55. So not equilateral, not equiangular. There's your little note there for what equilateral means. The last, letter C says triangle ABC is scalene. Triangle ABC, well, this angle is 60, this angle is 35, and this angle that's here, this is part of triangle ABC, was, if you'll recall, this was 30 and 55, this was 85. It seems like all of these angles are different measures. Since all the angles are different, that means all the sides are different. That means that, in fact, this triangle is scalene. So letter C is a check mark. There's your quick reminder there. Scalene means all sides different and all angles different. Next, we're going to go to the measure of angle ABD is 85. ABD is over here from A to B to D. This angle in here, it's not 85. This angle in here is 30. So this is actually incorrect, right? I will highlight where ABD is. Highlighter tool. From A to B to D, here's A, B, and D. So the angle ABD is here. Just this piece, not including that. So that's ABD, that's only 30 degrees. Okay, next, a triangle ABD. Go back to the marker tool. Triangle ABD is isosceles. We have from A to B to D a 35 degree angle, a 30 degree angle at 115. Unfortunately, this 35 and this 30 are not the same. That means that the triangle is not isosceles. If you'll recall, isosceles means it has two congruent sides and two congruent base angles. These base angles are not equal to each other. They're not congruent. And there's your note for isosceles. It means two congruent sides and two congruent base angles, but 35 and 30 are not the same. Last but not least, triangle ABC, which is from A to B to C, the big triangle now, is obtuse and right. Well, first of all, obtuse means over 90 degrees. Right means equal to 90 degrees. So there's no way any triangle could be obtuse and right at the same time. It doesn't matter what the diagram says, because obtuse means one angle is going to be greater than 90. Right means one angle is equal to 90. And if you were to add these two numbers together, you get over 180 already, and the triangle sum theorems as well. You can't have three angles that are more than 180 in a triangle. Okay, so that does not work. Let's move on to number 8. In the accompanying diagram, it says ABC is an equilateral triangle. We're going to label where it says equilateral triangle. ABC means from A to B to C. All of these angles, all of these sides are the same, and all of these angles are the same. It also means that every angle is going to be equal to 60 degrees, and I'll show you why. The triangle sum theorem says that all the three angles in a triangle have to equal up to 180. Well, each of these individual angles here then have to be equal to each other, so we can call them x, right? This is x, and this is x. That means that all three x's, or 3x, is equal to 180. In order to solve that equation, we're going to divide both sides by 3, and we should get 180 divided by 3, which is 60. So all of these angles are going to be 60 degrees. X equals 60. Okay, so now we know that piece of information, 60 degrees, and it says that AD is congruent to AB, or equal to AB, I should say. AD is this line segment here, and AB already has one hash mark, so I feel comfortable with using one hash mark again. So these are all 60 degree angles. I'll label them like that. All right, so 60 degrees, and 60 degrees here. The next question, this question says, what is the value of x in degrees? You'll notice that x is over here, and it's not really connected to anything at present. But there's one thing you know about this triangle over here, which I'll call triangle BDA. Here's B to D, here's D to A, and then here is A to B. This is an isosceles triangle, an isosceles triangle. I know that because this side and this side are congruent to each other. That means that this angle and this angle are going to be congruent to each other. So at the very least, since this is x, I know that this is also x. This angle, we don't know anything about yet. We just know that this is the same and this is the same. But speaking of that bottom angle, angle DAB, I know that this is a straight line. This red line here is a straight line. So that means this straight line is split into two angles, this angle here and this angle here. And the sum of these two angles is equal to 180 because they are, of course, supplementary angles. So since they're supplementary, the two angles added together equal 180 right there along that straight line. So that's 60 degrees plus something is equal to 180. That means this angle down here is 120 degrees. Easy. Well, remember that this blue triangle exists? Well, since that blue triangle exists, that means that this angle plus this angle plus this angle is equal to 180. That's the triangle sum theorem. That's what we're going to use here. So x plus 120 is equal to 180. You can combine like terms to call this 2x plus 120 is equal to 180, and then solve that equation. So it turns out that when 2x plus 120 is equal to 180, subtracting 120 from both sides gives us 2x equals 60. Then dividing by 2 on both sides, x is equal to 30. That means this x is 30 and this x is 30. It asks what the value of x is in degrees, so we can say that x is equal to 30, but of course we have to say degrees. That's here. Boom. All right, question 9. In the diagram of ABC below, it says that AB is extended to point D. You remember this extension is going to mean it's an exterior angle. And there's a theorem that relates the two remote interior angles to the exterior angle of a triangle. It says that this angle here plus this angle here is equal to this exterior angle here. I'm going to write that down. So just reviewing the triangle, I have x plus 40 as one of my interiors. I have 3x plus 10 as my other interior. They're both remote interior. In other words, they're on the other side of the triangle than the exterior. And then this exterior angle is 6x, so we'll substitute that into the equation. Now I'll combine my like terms on the left-hand side. I'm going to get x plus 3x, which is 4x, and 40 plus 10, which is 50. That should be equal to 6x. I'm now going to try to get all the x's on one side and all the constants on the other side. So I'll subtract 4x from both sides, and I'm going to end up with 2x on the right-hand side and 50 on the left. And then I'm going to divide both sides by 2, and I should get x is equal to 25. All right, so I should be able to go over to, wait a second, it's not asking for the measure of x or the value of x. It's asking for what is CAB. And you know that CAB is this angle here, x plus 40. So we're going to substitute the value of x, which is 25, into the expression here, and we get x is equal to, that CAB is equal to 65. Not too bad. We're moving on to question 10. A regular hexagon is rotated in a counterclockwise direction around its center. This is from the unit about transformations. Determine and state the minimum number of degrees in the rotation such that the hexagon will coincide with itself, otherwise known as map onto itself, also otherwise known as overlapping. So in order to take that hexagon and rotate it so that it coincides with itself, let's take a look at what a hexagon looks like. So here's a hexagon. It's got 6 sides. So I want to rotate in a counterclockwise direction. That's this way. Rotating it so that it maps exactly onto itself like that. Like it has that horizontal line on the top again. So how many degrees is, boom, that rotation? Well, it's hard to tell just by doing it on the paper, but there's a formula for it, luckily for us. So the angle of rotation, the minimum angle of rotation is equal to 360 divided by n. N is going to be the number of sides, and as you recall, a hexagon has 6 sides, right? We said it has 6 sides. So n is equal to 6. Our angle of rotation then should be 360 divided by 6. Let's move this over so you can see the whole thing here. So we're going to do 360 divided by 6. That should be equal to 60 degrees, right? So every 60 degrees I turn this thing, I'm going to map it onto itself. So we're looking for the minimum number of degrees. Well, that means if I turn it by 60 degrees, it's going to give us the hexagon coinciding with itself, mapping onto itself, overlapping on itself. So this here is the answer to this question. However, take heed that I could also rotate it another 60 degrees, boom, and it still coincides. And another 60 degrees, boom, and it still coincides. And another 60 degrees, boom, and it still coincides. So if the question was asking what are all the degrees in the rotation, such that the hexagon maps onto itself or overlaps on itself, it's not just 60. The possible angles of rotation are 60, and then another 60 for 120, right? We did, 60 plus 60. Then another 60 for 180, another 60 for 240, another 60. I'm just adding 60 every time for 300. I'm not going to represent it as 360 because every single shape that was ever made, if you rotate it 360 degrees, it overlaps itself. So we never say that 360. Every time you do this, if you do it correctly, you should be adding numbers until the end, which is going to be 360, and you never write the 360. Okay, moving on to the next question, asking the calculator to please kindly move out of the way. Question 11, it tells you the endpoints of BC, which are 5, 1, and -3, -2. We're going to do a transformation of R, which is that big R's rotation of 90 degrees. And a rotation of 90 degrees counterclockwise has this rule. We're going to take x, y, and turn it into -y, x. So B is 5, 1. This is called the pre-image. It's the original point. Now we need to find B prime, which is the image. C, which is -3, -2, we need to find C prime, which is the image of C under this transformation. Let's do it one at a time. And really slow down and make sure that this makes sense to you, right? B is 5, 1. So what I'm going to do, according to this rule, is I'm going to take the x value and put it at the end, keep the same sign. And then we're going to take the y value of the point, the pre-image, and I'm going to bring it to the front and change its sign to its opposite sign. So 5, which is the x value, it's going to go to the end of the new point, the image, right? And then the 1 is going to become the first value, but I'm going to change its value from positive to negative, right? So B to B prime, 5, 1 becomes -1, 5. That's how we do it for the B. Now check out how we did it here, right? The original point, the pre-image was C, which was -3, -2. That's from here. I'm going to take the x value, bring it to the end, and keep its sign. So -3 stays -3, but just goes to the end of the point. The y value of the original point, in this case is -2, is going to go to the front of the new point, the front of the image, and it's going to change its sign. Start off as -2, comes to the front, and changes its sign to +2. This is called a transformation, a rotation of 90 degrees counterclockwise. Moving on, what are the coordinates of P prime, which is P, -4, 0, under the translation x minus 3, y plus 6. This is a translation, which means a slide. That means what I'm going to do is subtract 3 from the x value. I'm going to add 6 to the y value. So first, that x value is going to be subtracted by 3, so -4 is going to be subtracted by 3. That gives us -7. The next, it says y value gets added by 6, so 0 plus 6 gives us 6. That means the new point, which is, of course, P prime, is -7, 6. -7, 6 is this first answer choice. Moving on. Question 13, under which transformation would A prime, B prime, C prime, which is the image of ABC, not be congruent to ABC? Congruent means same measure, or of equal measure. Now, the only time that a transformation is going to make shapes of not equal measure is if the shape gets bigger or smaller, stretching or shrinking. Reflection does not stretch or shrink, so we're going to keep that one the same. Rotation does not stretch or shrink. A rotation is just turning it. Translation is sliding it, so it does not change the size. But dilation is the one that changes it, right? A dilation makes things bigger or smaller. A dilation with a scale factor of 2, this number is larger than 1, so that means dilation getting bigger. This is stretching. Anytime we dilate a shape, it changes its size, and it is no longer congruent, no longer the same measures. So answer 4 is correct. All right, looking at to question 14, actually, let's talk about this real quick. All three of these, reflections, rotations, and translations, all share the same quality. They don't change the shape or size of the original image, the pre-image, so we're going to call them so-called rigid transformations. So that's the case for all three of these, reflections, rotations, and translations. The only one that's different in the transformations unit was dilations. Dilations are stretching and shrinking. They do not keep the size the same. The shape stays the same, but the size changes. Okay, good. Question 14, it gives us a composition of transformations. So we're taking A, B, C and turning it into A double prime, B double prime, C double prime. That means two different transformations happened. That's what these two little lines mean. What composition of transformations was used? The very first thing I want to look at is the pre-image versus the image, right? The image is the new version, right? So it looks like from the pre-image to image, the shape got smaller, right? It shrank. So that means the dilation should be something in between 0 and 1, right? The dilation should be of a fraction. I see dilation of 2 here, and a dilation of 2 is not going to cut it because it's taking a pre-image and turning it into a smaller image. Dilation of 2 means multiplying everything by 2, so that's not it. Same thing here, dilation of 2 is not going to do it because the dilation of 2 would be getting bigger, and this image is smaller. Okay, great. The last thing I have to figure out is which rotation went on, because both of these dilations are of 1/2. That means they shrank. A rotation of 180 degrees means it swung around twice around the origin, right? And a rotation of 90 means it swung around once around the origin. Now, just to give you an idea, this is what a rotation of 90 degrees would look like, right? We've rotated it 90 degrees, 1 quadrant around, and this rotation of 90 degrees brought it here to the 2nd quadrant. I think you'll agree that the image is not in the 2nd quadrant, it's in the 3rd quadrant. If we rotate it another 90 degrees, that's 180 degrees total, that would give us this, this triangle's location. So it looks like it's going to be a rotation of 180 degrees, not of 90 degrees. Okay, great. Moving on to the next question. This is a proof. I'm going to write down the full proof on the bottom here, and you can take a look at how it is solved. Oh, psych, just kidding. I'm not going to give you the proof. This is going to be something for class. But for each pair of triangles, we're going to tell which postulates make the triangles congruent. Let's go through them one at a time. It looks like I have a triple set of marks here and a triple set of marks here. We have the single set of marks here and here. And for whatever reason, it looks like it swiveled here on the diagram, but we have the double set of marks here, and there should be a double set of marks here as well. So I'm looking at 3 pairs of congruent sides, so this should be the side-side-side postulate. You could call it the side-side-side method, the side-side-side reason, but it doesn't really matter what you call it as long as you call it side-side-side. Here we have a couple of marks, right? We have this pair of sides, another pair of sides, and nothing else is marked on the diagram. However, I know that these 2 pairs of angles, this angle here and this angle here, are so-called vertical angles. And just in case you forgot, vertical angles, they share a vertex, they form opposite angles, right? These are opposite angles to each other, and they are congruent. So it looks like I have a pair of sides, and then a pair of angles, and a pair of sides. So this postulate is going to be side, angle, side. The angle is included or between the 2 angles, between the 2 sides, I should say. So side, angle, side. Next up here, I'm going to take a look at number 19. It says that these 2 triangles are congruent to each other. Let's see why. I have a situation where these are 2 right triangles. The 2 right triangles are right triangles because of these right angles. And I also have these 2 sides that are congruent to each other. For whatever reason, the diagram does not have the markings that are down here. I'll add in the markings for you. These markings are supposed to be there as well. We're supposed to say that these 2 sides are congruent. So I have these 2 sides. And these 2 sides, that's 2 pairs of sides, and an angle. So you might think to yourself, oh, it should be side, angle, side. However, I have this side, and the angle that's over here. Notice that that angle is not included in those 2 sides. So I could say this pair of angles, and this pair of sides, and then this pair of sides, but no, I shouldn't say that because that spells out a bad word. So instead, we are going to use the method that we can only use for right angles, right triangles, and that method is called hyp-leg, which of course stands for hypotenuse-leg. We have a hypotenuse of a right triangle paired up with another one, and then a leg of a right triangle paired up with another one. Done. Last but not least, we have RTS and CBA. You can see that this is supposed to be 2 arcs here, and this is supposed to be 1 arc here. Same thing here, 1 arc here and 2 arcs here. And you also know that we have AB and ST that are congruent to each other. So how are we going to prove this? Well, we have this pair of angles and this pair of angles and a side that is not included, a side that's not between them. So instead of saying SAA, we have a special formula for this, a special method for this. This one is called AAS. We're calling AAS method. All right, moving on to the next page here. Which set cannot represent the lengths of the sides of a triangle? We have 3 different lengths in each set, and we have to figure out which one is not a good triangle. Now, if you'll recall, the triangle inequality tells us that the small side plus the medium side of any triangle has to be bigger than the larger side. The reason is because if I make a triangle where the small side plus the medium side is equal to the larger side of the triangle, that's not a triangle, that's just a straight line. And if the small plus the medium are smaller than the large side, then the 2 sides don't connect. It would look like this, right? The longest side is here. If the small and the medium side don't don't add up to larger than the larger side, then these two lines just would not connect. They would not be a correct triangle. So let's try out using that triangle inequality here for letter A. Let's see. 3 plus 6 is 9, and 9 is smaller than 10. Looks like this set of sides is not going to work for the sides of a triangle, right? Because the two smaller sides have to add together to be bigger than 10, and 3 plus 6, which is 9, is smaller than 10. So this one's not going to work. But then for letter B, we have 2, 4, and 7. Let's see if this triangle inequality is going to work. Well, the small side was 2, the medium side was 4, 2 and 4 is 6. 6 is less than 7. So this also does not work for the length of the sides of a triangle. How about 11, 11, and 23? Let's try that one with the triangle inequality. Since both these sides are the same, we can interchange them between small and medium, doesn't matter, but 11 plus 11 is 22. 22 is in fact smaller than 23. So it looks like C will in fact also not work. So all of these three are not lengths of the sides of a triangle. The only one that does work is letter D, and I'll tell you why, because 7 plus 7 is 14, and that total, that 14, is definitely larger than 7. So that is the only one that works for the length of the sides of the triangle. Maybe we could rewrite this multiple choice problem for you when you come into class. Question 24, it talks about a scalene triangle, ABC. The measure of angle B is 45, angle C is 55. I'll bet you we could find that third angle just by doing a little triangle sum theorem. First, I'll give you that all you have to do is draw a little diagram. I have a 45-degree angle and a 55-degree angle. The next, I'm looking for angle A just to see which one is bigger and smaller, and we can use triangle sum theorem. I can say that the three angles of any triangle are equal to 180, so 45 and 55 together is 100. 100 taken away from 180 is 80, so this is an 80-degree angle. Bada bing, bada bing. Now it's asking for the sides, and I want you to be careful because what you have so far is not the side measures, but you only have the angle measures. So I don't want you to get confused here. We are going to use another concept about triangles, which is another part of the triangle inequality. Here's a fact about triangles that you should know. In any triangle, the longest side is opposite the largest angle, and the shortest side is opposite the smallest angle. I'm going to draw you a little picture to demonstrate this. If I make an angle that looks like this angle is pretty small, right? This angle down here is pretty small. So the distance between the two ends here is also pretty small. As I make this angle larger and larger and larger, the distance between these two sides, these 2 points, is getting larger and larger, right? So as the angle, this part down here, gets larger and larger and larger, that distance between the two endpoints gets larger and larger and larger. Okay, great. So that means I know that this angle A is the largest angle. So I'm going to label it with L, meaning largest angle. Boom. Boom. That means it's the largest angle. That means, of course, that it is across from the longest side. So it is across from that longest side. Here's our L, our longest side. The longest side is BC. So what is the order of the sides in length from longest to shortest? The longest side is BC, so the very first answer has to be BC. Oh, that's not it. Oh, BC, great. Oh, that's not it. Oh, BC, great. So the next angle has to be the medium. I'm sorry, the next side has to be the medium side, and the last side has to be the smallest side. Well, let's check the smallest side. The smallest angle is 45 degrees, so I'm going to say B is the smallest angle, and that smallest angle is supposed to be across from the shortest side. So this side, which is AC, is going to be the smallest side. That means if I'm looking at the order of the sides in length from longest to shortest, shortest should be the last. AC is the shortest. Looks like AC is last here. There's our answer. Very good. Question 25, in the set of axes below, it tells us some ordered pairs for D, E, and F, and then it's asking about midpoints of EF and midpoints of DF, finding out the coordinates of G and H. So I'm going to show you how to find these midpoints. The next part says we're trying to prove that a couple things are the case, but I'm going to just find the midpoints for you here. You'll recall that the midpoint formula is x1 plus x2 over 2, y1 plus y2 over 2. So if I'm trying to find the midpoint of EF, let's try to find the midpoint of EF first. G is the midpoint of EF. So I'm going to be looking at point E and point F. This is my x1, y1. This is my x2, y2. So I'm using the midpoint formula here. I am looking for G, which is the midpoint, so I'm calling it G, not M, so I can know what I'm talking about in this problem. So G is going to be negative 2 plus 8 over 2, 2 plus negative 2 over 2, solving these, I get 3, 0. I'm going to do the same thing for point H. H is the midpoint of DF. Sorry, I'm supposed to be using a different color. H is the midpoint of DF. That means I'm looking now at D and F. So now I'm going to change my x1, y1, and x2, y2 because this is now my first point, D, and this is my second point, F. So you can see I labeled them here, x1, y1, x2, y2, right? So now I'm going to use the same formula, but I'm going to use H instead of M because H is the midpoint that I'm looking for here. All right, so you'll see here that I did -4 plus 8, -4 plus -2, right? I'm using the y1 and y2, the x1 and the x2, and that is labeled in blue. 4 over 2 and -6 over 2, that should give you 2, 3. That's my midpoints. Okay, moving on to the last page here. In each figure, it asks you to state the name of the point of concurrency shown in the constructions that form the triangle center. It's basically just saying, what are these lines and what points do they form? Well, let's name them one at a time. Well, in this case, these lines are all altitudes. I know they're altitudes because I have a right angle here. They're all perpendicular to the base, and they intersect the vertex, right? Those are the 2 requirements for altitudes. So all of these lines are altitudes. There's a name for the point at which all 3 altitudes intersect, and that point is here, and it's called the orthocenter. Next, this diagram has not altitudes, but another type of line drawn here. These are all medians. They intersect the midpoint of sides, and I know that this is a midpoint of sides because both of the pieces that it cuts the side into are congruent. And they also intersect the vertex, right? So it intersects here and here and here respectively. And there's a special name for the point at which all the medians intersect, and that point is here. It is called a centroid. Right? So altitudes all meet at an orthocenter, medians all meet at a centroid. For the next picture, I have a right angle similar to what I had for altitudes, but you'll notice that these lines don't necessarily have to hit the vertex, but they are hitting a point that is a midpoint of the base. So these ones are known as perpendicular bisectors, right? They are perpendicular to the base. I should be using the green color here. They're perpendicular to the base, and they also intersect the base at its midpoint. How do I know this is the midpoint? Because this piece and this piece are congruent to each other. There's a special name for that point at which all 3 perpendicular bisectors intersect, and that point and that word is circumcenter, right? The circumcenter is where all perpendicular bisectors intersect. Well, last but not least, you can see that there is a small difference here because they do intersect at vertices, right? They intersect the vertex of each of the sides. We're going to use, we are using purple for this, but they don't necessarily meet at a midpoint, but what they do is cut the angles in half. So all of these lines are called angle bisectors, and that special name for the point at which all the angle bisectors meet, well, that word is incenter, right? The incenter is where all the angle bisectors meet. There's a quick and easy way to remember all of these terms, and that quick and easy way is all of my children are bringing in peanut butter cookies. So why does this work? Because A stands for altitudes, O stands for orthocenter, my stands for medians, children, the C stands for centroids. Switching it up here a little bit, are bringing, that's AB angle bisectors, in centers. And then last but not least in green, PB is peanut butter, also known as perpendicular bisectors, and cookies indicates circumcenter. That's the way that we use, that's the initialism that we use to try to remember that. All right, let's see, we're skipping 27. We are going on to, this is the last question that we do in the video. How sweet. This was a video on the Interim Assessment 2 review. We're going to be doing some of the questions that we skipped on the video in class, but just please be prepared for that. All right, folks, long video, but good luck studying.